In today's video, we're going to be talking about series circuits. After this video, you should be able to calculate the current, resistance, and voltage drops at different parts in a series circuit. And then really another side thing to this is you should be able to, again, be able to distinguish between how a series circuit would be different than, say, a parallel circuit, which I will have a video on right after this one. All right, so let's get right to it. A series circuit, remember, a series circuit is when all the devices in a circuit are connected in a series, okay? And so basically what that means is each device is connected in a manner that each charge will pass through each resistor in a consecutive fashion. Okay, so we've been learning about symbols in a circuit, and so if this is my battery here, and if I were to draw a series circuit, and I were just to say draw 3 resistors in my circuit, this would be an example of a series circuit. Basically, the path at which charge flows through the circuit, they're going to have to go through all 3 resistors. There is no other way to go through this circuit without going through all 3 of them. And that's, by definition, a series circuit. So the resistance in a series circuit and the current in a series circuit is what we're going to be talking about here. Basically, charge flows together through the external circuit at a rate that is the same everywhere. Okay, so the current is the same everywhere in a series circuit. So the current is not greater at one point or smaller at another point, it's the same. And that's huge in solving a lot of series circuit problems that I could throw at you. The resistance in a series circuit, as you add more and more resistors, the resistance continues to get bigger and bigger. Okay, so if I were to put 2 6-ohm resistors in a series circuit, that would be like the equivalent of having one 12-ohm resistor in that same circuit. Okay, and that is known as the equivalent resistance, which is going to be a formula that we're going to talk about in the very next slide. But again, in a nutshell, basically, the current is the same everywhere in a series circuit. But the resistance, as you add more and more resistors to the circuit, it gets to be higher and higher and higher, or more and more. Okay, so let's talk about resistance a little bit. This is the equation for a series circuit to calculate the total resistance in the circuit, the total resistance in the circuit. And this is going to be an important equation, so you'll definitely want to have this down. So the total resistance is equal to the first resistor plus the second resistor, plus the third resistor, and you just keep adding however many resistors you have in there. I mean, if you have 20 resistors in the circuit, you're going to add each and every single one of those resistors up until you get the total resistance. Okay, so just for instance, if I were to say draw a circuit here, and if we go back to my example from my previous slide, let's say this is a 6-ohm resistor here, and this is a 6-ohm resistor here. The total resistance, or the total R, would be 12 ohms. I just took 6 plus 6 and added it together to get 12 ohms. Okay. The current in a series circuit is the same everywhere. And like I said, that's going to be really important. Once you figure out the current, you know it everywhere in the circuit. It does not change. So charge does not pile up and accumulate at a given point in a circuit. And so the formula for that is the current from the battery is equal to the current at like 0.1, is equal to the current at 0.2, is equal to the current at 0.3, and so on. Okay, so the current is the same everywhere. All right, and so the current at the first resistor is the same as the current at the second resistor, and so forth. Okay, so the current, same everywhere. There are voltage drops in a series circuit. Remember, voltage is just a measure of basically the potential difference at a point in a circuit. And a voltage drop occurs when electrical energy changes form. So either in the form of heat, light, whatever the case may be, mechanical energy, all right? And so if you have a 1.5 volt battery in a series circuit, there's going to be a voltage drop for each resistor. But the sum of all those resistors cannot be more than 1.5 volts. So basically what it's saying is the battery is putting 1.5 volts into this circuit. You can't have a bigger voltage drop than that. It must add up to 1.5 volts, okay? Because you can't just make energy out of nothing. Okay, so that can be written as the total voltage in the battery is equal to the voltage drop at 0.1 plus the voltage drop at point 2 plus the voltage drop at point 3. And I'll do some examples with this in a bit, but just keep in mind that the voltage drops at the various points in the circuit has to add up to being what the voltage of the battery is that you're using. So here's an example, okay? I have 120 volts here, which is pretty big, okay, 120 volts, and I have 2 light bulbs. This light bulb uses up 80 volts. How much is left for this light bulb? Well, the total voltage drop is the voltage of the battery, which is then equal to these 2 voltages, 80 plus unknown, okay? And the battery voltage is 120 volts. So I have 120 volts equals 80 volts plus, I don't know, what equals 120? Well, this has got to be 40 volts. So basically what it means is by the time the circuit is complete, it has used up all 120 volts and it's ready to be recharged again by the battery, or to regain energy, I should really say, by the battery to then go through the circuit once more. Okay, here's another example. 12 volt battery is equal to a 3 volt light bulb plus unknown voltage plus this 4 volt light bulb. Okay, so basically what we have is 12 volts equals 7 volts plus question mark, right? Because I just added 3 plus 4, that equals 7. So I'm just going to subtract 7 from this side, and I would get that this question mark must be 5 volts to complete this problem, to make this problem true. And so this must be a 5 volt drop here at this light bulb. Okay, so that's kind of how that formula works. So again, I've been using this skier analogy. Hopefully it's useful, but basically the idea here is that at the battery, this is the ski lift, okay, and that's what's giving the skiers energy to then go back down the hill and you know, enjoy their skiing trip. Basically what you can kind of figure is the wire is flat points on their way down the hill, and then the resistors, I know in the previous video I had said this was like a hot chocolate shop. For today, I'm going to pretend that this is like a hill. Okay, so basically the skiers are going along a flat area, and then all of a sudden at a voltage drop, they go down a hill and they lose some of their energy. Okay, so this would be a point where they lose energy, and that energy is lost typically to either light or heat or mechanical energy or whatever the case may be. Okay, and in terms of the skiing thing, they're losing it to kinetic energy, right? They're gaining speed by going down the hill, and then now they're at a flat point and they travel along, and then all of a sudden they hit another resistor, and so they hit another hill. Okay, and they head down the hill and they gain more speed, and then they keep going along a flat point, and then they hit another hill. And then finally they're back at ground level to then be taken back up the ski lift to then repeat the process again. Okay, and if I were to graph that, the skiers start at a potential energy of 12 volts. Okay, and then from point A to B, there is no loss in voltage. Okay, from point A to B, there's no loss in voltage. But then from B to C, they hit a hill and they lose energy. It drops down. And then from C to D, it's flat. And then D to E, they hit a hill, and so they lose energy. And then E to F is flat, and then F to G, they hit another hill, and they lose more energy. So I don't know if this skier analogy is useful to you, but then again, here's the ski lift. They come back, and they repeat the process. It just keeps going over and over again. Okay, so look at resistors as a way of basically eating up energy or using energy, and they call that a voltage drop. So this is the type of problem that I could ask you about a series circuit. I'm just going to quickly change my pen color here just to do something a little different. Let's go with yellow. Okay. Here in this circuit, you can see that we have a battery with a total voltage of 60 volts. Okay, and there are 3 resistors in this circuit: a 17 ohm resistor, a 12 ohm resistor, and a 11 ohm resistor. The first thing that I'm going to want to do is I'm going to want to figure out what is the current in this circuit. Okay, actually before I even do that, I want to first figure out what is the total resistance in this circuit. And if you remember, there is a formula where it says R equivalent, the total resistance, is equal to R1 plus R2 plus R3. And R1 is 17 ohms plus R2, which is 12 ohms, plus R3, which is 11 ohms. And if you add that all up, you should get an equivalent resistance of 40 ohms. Okay, that's important. All right, so basically, by the time the 60 volts gets used up as it goes through this whole course, it's going to have gone through 40 ohms of resistance. Now, one of the big keys to solving, basically, I want to know what the current is at each of these resistors, and I would like to know what the voltage drop at each of these resistors is. The big key to figuring that out is, first, we need to find out the current. And the reason why I want to find that out is because, remember, in a series circuit, the current is the same everywhere. Okay, so I can figure that out by using something called Ohm's law, which this should be a refresher from a couple lessons ago. V equals I times R. Well, I'm trying to find I, so I'm going to get I by itself, and I'm going to have I equals V over R. Do I know the voltage of this circuit? And the answer is yes, it's 60. And do I know the total resistance of this circuit? And the answer is yes, it's 40 ohms. So if you do 60 divided by 40, you should get 1.5 amps. All right, so the current in this circuit is 1.5 amps. Okay, and that's everywhere. Everywhere in the circuit, there's 1.5 amps of current flowing through it. Now, I'm wondering what the, and there's all these boxes to fill this all out. I'm going to just keep it down here in the dark area just so that you guys can actually see my writing. But I'm going to first start with this one right here, resistor 1. Okay, I'm wondering what the voltage drop is at resistor 1. Okay, and so I'm going to again use Ohm's law, V equals I times R. And I know the resistance at this resistor is 17 ohms. I know the current at that resistor is 1.5 amps. Which we just found right there. And if you do that math problem, 1.5 times 17, you should get an answer of 25.5 volts. Okay, and this is R1, 25.5 volts. Okay, so there's about 25 and a half voltage drop just at that one resistor. Now I'm wondering what the voltage drop is at resistor 2. Well, to do that, I'm going to use the same formula, Ohm's law, V equals I times R, where I is 1.5 amps, times R, which is 12 ohms. And if you do that math problem, V equals I times R. If you do that math problem, at R2, the voltage would be 18 volts. 18 volts. Okay, so there would be a voltage drop of 18 volts at R2. Okay, now the last one is R3. What is the voltage drop at R3? Well, I'm going to do the same exact formula, V equals I times R, where I is 1.5 times R, which is 11. And this is V. V equals 1.5 times 11. And I'm going to put the answer up here since I'm kind of running out of space. So R3 would equal 1.5 times 11 is 16.5 volts. Okay. So what did I just do? Well, first I started off by figuring out the total resistance of this circuit, and I just added 17 plus 12 plus 11 to get 40. Then I wanted to find out the current of this circuit. So I used Ohm's law, V equals I times R, and I took 60 volts, which is from my battery, divided by the total resistance, which is 40, to get 1.5. Once I knew the current, I knew that the current everywhere in this circuit was 1.5 amps. And so then I could start plugging that into Ohm's law using these different resistances to figure out the voltage drop at the 3 different resistors. And one quick way you can check this is we know that by the time this charge has gone through this entire circuit, it should have lost 60 volts of energy. And so if I add R1 plus R2 plus R3 up, and if you do that, you should find out that the total change in voltage would actually equal 60 volts. And if we compare that to the voltage of our battery, 60 volts, we know we did this answer correct. Okay, and things are looking good. If this is confusing, don't worry. I promise we'll do example problems in class and we'll get this hammered out. But this isn't just to give you an idea of what I would expect you to be able to do with a series circuit. That takes care of today's video. I will see you guys next time.